So today's agenda discusses the learning methodology we are supposed to follow in the sessions to come. Okay, so how is that? Let's first discuss something that is very important. What is the difference between data science and machine learning? And let's compare them to data mining. Like, these three terms are somehow used interchangeably within specific contexts. And it is very important to outline the differences between all three. So let's first discuss the difference between data science versus ML versus DM, data mining. Okay. So let's first say that the DS is associated with an entire workflow. This is the entire workflow we have. ML is a part of that workflow, which is related to modeling predictions. Data mining is an entire workflow as well. It could be conjoined well with the data science. But then again, it is not an entire workflow that uses modeling predictions within it necessarily, but it's an entire workflow that may use modeling predictions among other stuff so as to extract knowledge from the data. So DM is all about knowledge extraction from our data as a whole. But here we have modeling predictions for each data point individually. So this is the most important difference between the ML that is done in the data science workflow or the ML that is to be done in the DM workflow. Because make no mistake, this is also an entire workflow. But knowledge extraction oriented. I mean, from our data as a whole. But here we have an entire workflow with the data science, but it is modeling prediction oriented. Using each data point individually. So a data mining process or workflow can use machine learning within it, but not to actually be able to predict something. Even though the machine learning model learns to predict individual data points, but I use it not for this end, but to represent feature importances in driving my predictions. So right now I'm talking about predictions and the factors that drive them through the entire data set. This makes it a data mining problem. So data mining is whatever process I may use within a specific workflow that allows me to get knowledge about the entirety of the data set that is in front of me. Whereas data science focuses on modeling predictions. And this is where the ML could be used in either of these. So machine learning, let's say it's like a kitchen. So a kitchen may work to serve the restaurant needs, but the restaurant always controls the guidelines that the kitchen has to follow. It always controls the domain in which the kitchen operates. And in that sense, the business needs of the restaurant dictate what kind of a kitchen I'm going to have. In the same manner, data science problem or the data mining problem, what they are simply characterized by is the business context. And the ML does not have a business context on its own. So in the data science cycle or the DM cycle, I get to use the entire workflow, which is starting primarily with the business understanding or the business context. This is a very important term that we should discuss. So in that sense, we should say DS/DM workflow. So the entire workflow is divided into two parts: business understanding and business logic. Business logic is a common term in software development, which simply means when I click this button, what happens in the system underneath to react so as to serve, okay, I did X and the system has to respond with a Y. What is given between that is the business logic itself. And the business understanding is what I did to plan out this business logic. So the workflow here is comprised of two main parts. Business understanding and business logic. Okay, so business understanding is the strategic planning layer. And the business logic is the operational layer. So let's see. The business understanding, for example, dictates that I should develop an auto speaker recognition algorithm. So in that sense, I'm having something like a door lock that gets activated or that allows someone to pass through the door if his voice print matches what is stored inside the system. Okay, so this person can enter the house and those people cannot enter the house. So in that sense, this kind of problem, it has a lot of business understanding actually. The business understanding in that sense is not related to money or the service being deployed. Yes, it is related to that, but this is not the important thing. The important thing within the business understanding is something called domain knowledge. So a core component of the business understanding, especially for data science workflows, is domain knowledge. Let's first discuss the business understanding aspect and then move on to the domain knowledge and you'll get what I mean. Business understanding is like I'm developing an auto speaker recognition algorithm. In that sense, the word auto means that the algorithm has to continuously record the audio that is occurring around the microphone and does a fast Fourier transform to get its frequency spectrum, and depending on the magnitudes at several frequencies we get to determine the spectral centroid, which is the average frequency around which the average energy is being given. And in that sense, this spectral centroid, believe it or not, is the average frequency of the signal when in ambience, and this is always much lower than a speaker actually speaking directly into the microphone. So if you find the noise of some people in the background, this actually has a lower spectral centroid than someone who is directly speaking into the microphone. So this is a very helpful bit of information that, okay, so I will continuously record, and in that sense, the last maybe 200 milliseconds, I will convert what is equivalent to them in samples to the frequency domain to determine the spectral centroid, and this is to be done through the ambience, and this is my baseline. Whenever someone gets to speak, then the spectral centroid suddenly becomes higher, and it goes over that adaptive threshold of the ambience around me. In that sense, I get to not throw into a buffer and throw this away afterward, but store it in a buffer with an intention to actually take it afterward and convert them to a representation that models the human ear mathematically. In that sense, when feeding this kind of samples into a mathematical algorithm, the output would be how a human ear should hear those voices, which is basically MFCC, mel frequency capsular coefficients. This is what this method entails someone to do from a philosophical standpoint. So all of this is business understanding. The domain knowledge is actually understanding what is the physical nature of the MFCC. Okay, it's modeling the human ear using a computer algorithm. So this is very beautiful. Like, I have to go through this detail, but you have to go through the journey with me. And yeah, it's really fun, actually. So there's a cochlea within the ear that's deep within, and basically it has like those hairs that get excited by a specific fluid that gets actuated by the eardrum. There's turbulence within that fluid when the eardrum vibrates, and those strands get connected directly to the nervous system, and based upon their vibration, I'm able to hear this voice. So there was Wecker in the last century. He made this modeling of the human ear, and he divided it into 24 areas, where each area has its own average frequency that gets to be excited. And the frequency is not measured in hertz in that method, it's measured in Mel scale, which is a scale that could be perceived as linear to the human perception. But then again, like, this is all business understanding for my model, like about this buffer, and when I get the spectral centroid higher, and I have to use MFCC. This is all business understanding, and the bits of domain knowledge lie in the spectral centroid of the ambience is much lower than someone who is directly speaking into the speaker. This bit of information is domain knowledge. It drives your innovation forward. Okay, and it varies from science to science, from discipline to discipline, and machine learning is supposed to be complementary to all disciplines. God willing, yeah. Okay, so in that sense, we have, for example, the Mel scale and the human perception of it rather than the Hertz scale. This is domain knowledge, okay? The MFCC being like a method to model the human ear mathematically. This also is a domain knowledge. So domain knowledge is more like studying the auditory system from an anatomical standpoint to be able actually to come up with an algorithm. So it's much like theory, but in a different field that could propel your creativity to actually find a solution. So it's really beautiful, and it basically goes everywhere. Like, I was developing this algorithm about sprinkler systems, and through different sprinkler configurations, I get to tune them to produce high uniformity metrics without actually going to the field and trying this out for myself. I just do one experiment on a single sprinkler and tile it all over a specific zone and get to measure the efficiency and the uniformity. So basically that has a lot of domain knowledge from a landscaping specialist and maybe an agricultural domain knowledge expert. So this is the domain knowledge. This is what you consult with others when developing custom software for them. But in machine learning, it takes a whole new meaning. So this is beautiful, actually. Like, science is a great gift. So in that sense, we discussed the business understanding and its core component, domain knowledge. The business logic is actually typing the code to actually do all of what we talked about. And that's it, okay? So in that sense, this is the operational layer. Okay, but in data science and data mining workflows, the business logic needs to be a little bit more verbose. So let's go to something called CRISP-DM framework. So what is CRISP-DM framework? Basically, a CRISP-DM framework is called cross-industry standard process. for data mining. Okay, so this is a framework being developed to outline a workflow for a data mining process. And coincidentally, it could be applied to a data science process because they are inherently similar. The only difference between both is this is associated with singular data points, the data science, and the data mining is simply oriented towards the entirety of the data to extract patterns of the data, not for predictive purposes, but just for making decisions. That's the data mining part. So in that sense, let's discuss the phases of CRISP-DM framework, or CRISP-DS, but yeah, they never call it that way. Then again, first we have the business understanding. But in that area, it does not extend only to develop a machine learning model that does ASR, which is not auto speech recognition, auto speaker recognition, the voice print of the speaker. So basically, after I transform this data into its features, I get to explore those features, I get to clean those features, I get to model those features, and I get to make predictions with those features, and I get to make evaluation of such system. So basically, this is all the CRISP-DM framework. Okay, so the business understanding extends all the way from agreeing on a method to actually collect the data that I'll be working on, because I'm developing a predictive model. So in that sense, I need to actually gather the data for the model that best serves the interests of the consumers of my product that I'm seeking to develop, or the service that I'm seeking to broadcast through a website, for example. So in that sense, the business understanding goes all the way from collecting the data or selecting the suitable data, and goes all the way to understanding the domain knowledge of the data and how we should process it and how we should do everything about it. So this is all strategic planning. Okay, let's get the best data and get the best out of it. So, for example, in the ASR, we have something called text-independent speaker recognition, and we have text-dependent speaker recognition. These are two opposite seemingly fields or subfields, which are basically, one of them is associated with, which is the text-dependent, depends on the speech that I'm actually saying while determining my voice print, whereas the other one actually focuses solely on no speech at all. It focuses on the speaker characteristics of the person who's speaking. So in that sense, we get to have another bit of domain knowledge understanding, which is you can identify the speaker without saying any words, only if he is saying, or predominantly if he is uttering vowels, not consonants. So you may make that decision in the business understanding to actually pre-process the data to remove the consonants from it and keep the parts of speech that correspond to vowels. So basically the audio track wouldn't mean anything. Okay, it will be unintelligible, like it's saying ah, oo, e, u. In that sense, you get to determine the identity of the speaker, which is very good. But on the other hand, what do we have to do this? So domain knowledge-wise, it tells us that there is something called a spectrogram, which is an image that represents different frequencies and the magnitudes of the signal at those frequencies at different points in time. So basically, it's a 2D image, and in that sense, whenever the speaker is saying a vowel, there is something called formants, which we simply refer to as resonance in physics. So whenever you see parallel lines in a spectrogram, you understand that this is a formant and this is a vowel. So you are supposed to keep those, and anything else that doesn't contain those, you are supposed to trim them or to clip them. So it's really beautiful. The business understanding, it makes your work carry your own aspiration and aptitude towards being someone who is like really resourceful and not giving up. So this is only an exploratory session. What should come afterward are all exploratory. I'm not expecting anything from you. You get to learn at your own pace. You get to determine if this is the field for you. But this is every bit of awesome as it could be if you actually like it enough. So this is the business understanding part. Then again, there is another phase of understanding, okay? So when I process the audio data into MFCCs and I get to explore them a little bit more, I could find that maybe specific areas of the ear are not important enough in determining the identity of the speaker as others. So maybe I get to neglect those areas. That's on one hand. Maybe I'm seeking to do something like standardization, which is a process done to make the ranges of every feature similar to the other in MFCC. But if you have enough domain knowledge understanding, you will know that this would be disastrous. So let's add data understanding first. So like when I take a look at the data, I discover that it would be disastrous to actually do standardization to it. Why is that? Because with the data understanding, different areas of the ear have correlations between them. So this area of the ear gets excited and it correlates, its excitation correlates with another area. So they almost always get excited together by like similar amounts. So in that sense, discovering this correlation and understanding the inherent domain knowledge of the MFCC features, that they all represent very much the same quantity, which is the amplitude of the audio for specific areas in the ear or the cochlea, where each area is having specific frequencies. Knowing that all of these features practically have the same physical quantity being represented, and from the data understanding, we get to discover, okay, there's correlation between them. So basically they could be not dependent on one another, but they tend to change with one another quite a lot. So in that sense, there's a process called standardization in machine learning. Standardization in machine learning is pretty much common practice, where you actually, to train a machine learning model well, you have to normalize the range of every feature and make it the same as the other feature. Or not normalize the range, it's actually normalizing the variance. But there is covariance, where actually there's variance, there's variation within each feature on its own, and there's variation between two features. Like it could model a dispersion of points in 2D space. Okay, so in a 2D space, not on a single dimension, which is the variation or the variance, it's covariance. But if we do standardization, I know from domain knowledge that this actually messes up with my dispersion across 2D spaces of each two features. And in that sense, I know that doing this would ruin my data. Specifically in the context of audio features, MFCC features, okay? So in that sense, okay, maybe I should apply PCA first, okay, principal component analysis, where I get to actually derive new features from the MFCC features that are linear combinations of them in a way that makes the correlation between each two new features zero, and then I can apply the standardization. So when you understand everything about your problem, you are able to actually plan it. So data understanding is not as business understanding. It's more like, okay, business understanding, the core component of it in the CRISP-DM framework would be the domain knowledge, but the data understanding, the core component of it would be using statistical analysis to understand the data that is actually in front of me. And in that sense, I get to determine the strategy that I should deal with it. So I should not make a pre-processing step, determine it strategically, based on nothing but business understanding. Okay, I can use everything on the business, but I haven't seen the data yet. Okay, business is like having the data collected within it. But then again, the data understanding is actually discovering this data and discovering patterns within it, using visualizations within it, examining it statistically to make well-informed decisions about how I should clean this data, about how I should merge those features, given the example of the variance, covariance, and like the standardization and the PCA. Like these all are methods used in machine learning, and they all help our model to perform at its best. Okay, I need to prepare everything for the model, my little child, to do everything it can given the data it has to deliver the best results. Okay, so I'm not to use AutoML on everything and do little to nothing on pre-processing the data accordingly in a manner that suits the model. So basically, for example, I may have an SVM model, a support vector machine model. This type of model is actually very tricky to train and tune, even though it is very complex. Like it's complicated enough to be smart to actually understand the patterns within the data in order to make a prediction. But then again, it's if you don't know one thing about it, is that its core characteristic is that it depends on measuring distances between data points to determine their similarity. So there is a little bit of like something that we have in machine learning called like we could mention statements that actually may have no meaning for us because we haven't tried them before, but they are like, okay, they are taken for granted, but we will try to explore them a little bit further. Basically, it says that when the dimensions increase, the distance measurements get to saturate. So distant points and close points could have similar distances to a specific point. And henceforth, my similarity measurements and hence my training of the SVM model could be wasted. So I wouldn't be getting the best out of it. So I need to minimize those features first. So I get to use a method like the PCA to do so. And possibly standardization before it, not after it. Why? So this is all related to domain knowledge and business understanding. Okay, so this is the core of the CRISP-DM framework. This is what makes a good data scientist, a good machine learning engineer, is to go through all of these first. And yeah, machine learning is just like focusing on the modeling part of the CRISP-DM or the workflow that we discussed before. But then again, every machine learning engineer was once a data scientist, okay? And in that sense, he has to understand the entire workflow and the thought process to deal with a problem before he gets to choose the best machine learning model, or he gets to like conceptualize the best machine learning model for his needs. Maybe when every other model is not good enough, maybe in a professional research or an academic research that he has to come up with something that is very special. So in that sense, a machine learning engineer is already someone who is well versed in employing his mental faculties in coming up with a solution through domain knowledge. Let me give you a simple example of domain knowledge in a machine learning model that is strictly very high end. The BERT machine learning model is basically a transformer model that actually makes informed decisions on the text that I type, and it gets to respond accordingly through translation or through replies and discovering various topics, of course, as you already know that from LLMs. But then again, what's special about it was actually developing the multi-headed self-attention mechanism. The multi-headed self-attention mechanism is actually a mathematical formula that models the human attention to specific words whenever I am studying a subject that I am looking for answers within. Whenever I'm studying a specific subject, I have specific keywords that I use to look for an answer. And I have the topics that I'm searching through, and I'm having the queries, I'm having the questions that I'm trying to answer. And through the questions and the keywords and the documents that I'm browsing, I'm actually looking for the answer to specific statements. Someone said that when he was talking about how to conceptualize the multi-headed self-attention model. So he came up with an equation in linear algebra that does just that. So domain knowledge is the ability to employ your faculties in different fields, and if not, actually derive analogies from ways you seek to mathematically model something empirically, so that it could give us a specific good result. So the multi-headed self-attention model equation is not derived, it's actually conceptualized, okay? It's empirically proven to do good things, but it could be better. Basically, it all depends on the domain knowledge. There are, I believe, like about 9 or 11 types of attention mechanisms. So yeah, it's a very good thing actually to try to explore. It's amazing. We're gonna do this together, God willing. Then again, the data understanding, business understanding, okay, data understanding, it's all right. And then we go forward to where exactly. So business understanding, how our data performs in real life, and data understanding, what our actual data like actually look like statistically when exploring it, and the various patterns within it in general. And then we have the third one, which is the data preparation. Okay, and we don't have to explain that. We clean those data points that look like anomalies. We remove those unnecessary features. We merge those features. We split out this feature into 4 different features. This could all be determined through business understanding and data understanding, okay? So in data preparation, I get to do feature selection. I get to do feature engineering, which is transforming different features into others that are meaningful within the domain knowledge or the business context. And on the other hand, I get to do feature extraction. So feature extraction is like feature engineering is to be done manually in accordance with the domain knowledge. Feature extraction is to be done mathematically through an algorithm that does that for us. So basically it applies to it could apply to thousands or hundreds of features, but this cannot be done manually in terms of feature engineering. And yeah, the anomalies in the data would be outliers. So basically an outlier in the data would be an apartment that gets sold for £1. This is practically an outlier, a business logic outlier actually, because no actual apartment is actually priced that way. And in a sense, so basically this data point could be dropped, could be substituted when cleaning the data, or it's like we may have something like 10,000 pounds, and basically an apartment could sell for 2 million in Egypt, for example. So in that sense, a whole apartment for 10,000 pounds? No, it's not like that. It's the price per meter squared. And in that sense, it is not a business logic outlier, but rather a data outlier. It's a data understanding outlier, because 10,000 is not mentioned a lot in the data set. So in that sense, and through domain knowledge, we understand that, okay, we can clean it by multiplying it with the area of the apartment itself, a normalized measurement for price over all apartments. So that's an example of a business-wise and a data-wise outlier. Okay, so that is data preparation. We have lots of things more than that. Like in data preparation, there are plethora of machine learning models in there that could be applied to process our data, actually. So it's really beautiful. Okay. Now, let's move forward with the modeling phase. So the modeling phase is basically the machine learning phase. It's as simple as that. You understand the model, you understand its theory, you understand everything that makes it tick, and in that sense, we get to prepare the data in a manner that, okay, that suits the data understanding and the business understanding well, but Also, the other half of the data preparation is to prepare the data in a manner so that the model performs at its best, the model that I chose for myself, okay, for this problem. Okay, so that's the modeling part. And now we get to move on to the fifth part, which is not the modeling, but the evaluation itself. So evaluating the model, maybe I have multiple models. So I prepared the data in the second half to make the model give me the best performance. And maybe I processed it in another manner to suit another machine learning model that I chose for myself, and a third one. And in that sense, I have three models and I have to compare them together. And in that sense, the evaluation works its way to determine the best machine learning model. Of course, in evaluation, we have many metrics. Yeah, so basically, the metric selection is based on the business understanding. So basically, if I have something like COVID and I'm looking at the symptoms and judging if or predicting if this person has COVID or not, then in that sense, a recall would be better. A recall is simply from the entirety of positive subjects, like having COVID, having contracted COVID already. How many did I get? Because if I got all of them, then this is good. If I missed one, then that could be a problem, okay? That could exponentially grow, and that could be a problem. So in that sense, recall is very important. So I'm not concerned with accuracy where I would get like, okay, how much did I get right from every data point in there? Like whether it was positive or negative diagnosis of COVID. No, I'm concerned with the positives and I want to get as much as I can. So in that sense, the evaluation works well in case of COVID with recall. In case of precision, for example, I have spam. So in that sense, precision would work best, which is simply, it does not seek to get every positive spam, but actually from the portion of the data that it said it was spam, how much did I get right? So in recall, I say, how much of the entirety of positively diagnosed patients did I get? But in case of spam, how much did I get, or how many did I get from the specific portion of people that I said they were positive spams? Okay, so in that sense, the first leaves no stone unturned. It needs to identify every patient with COVID. Okay, but in spam, the ones that I said they were spam, they have to be spam, because what would happen if this wasn't spam? An email that could hold a job offer for someone to get hidden in the junk box. And in that case, someone could lose a job opportunity. And if it were a spam to begin with, like, I'm not concerned with getting all the spams, because if it was a spam, the user is intelligent enough to understand that, okay, this is a spam, obviously, so I'm going to ignore it. So I could pass some, but for the greater good of saying, okay, if I said that this is spam, then this has to be a spam. But if I didn't say so, okay, the user can carry off after me. Okay, so precision and recall are different things. So they could be used to tune the model and choose the best model that I have. We have the F1 score, we have the ROC AUC score, and this one, we use it when we have similarly performing models. And in that sense, I want to determine which model is the most stable in terms of adaptability to adding new data. So basically, in the speaker recognition software, I could be having a cold one day. I could be wearing a tie, like basically constricting my trachea. And in that sense, like my speaker characteristic would be constricted in that area of the trachea, and in that sense I could be perceived differently by the machine learning model. But the machine learning model has to be adaptable enough to actually get this data, determine that I'm speaking in that data. If I pass, it gets to take that data and actually use it to adapt the model to the moments where my voice doesn't sound the way it is, due to illness, due to anything. Okay, so this is very important, guys. So The ROC AUC score, in that sense, when I adapt the model to new data points, basically I get to vary the threshold upon which I say that this is the right person or this is an imposter. I should like not let him inside the apartment using this door lock. And in that sense, the AUC score, as it gets higher, it determines which model is actually more robust to changing the threshold in case of adaptation with new data points added to the data. So AUC score is very important when the machine learning models are actually performing similarly in other metrics, okay? So yeah, this is just scraping the surface. We aim to discover a lot in that field, and it's really beautiful. And God willing. So evaluation, when we finish with that, we actually can go back to the business understanding if our results, no matter how we try tuning the model, are not good enough to serve our business context. And in that case, the business understanding, we should go back there and see what we might have missed in the domain knowledge in terms of processing the data. For example, removing the consonants and keeping the vowels. That could be a good strategy to actually make the evaluation even better the next time we try that. So I get to go all the way back to the business understanding phase or the data understanding phase and start from the beginning, okay? So this is very beautiful. And and if the evaluation turns out all right and I'm good to go for the business context that I'm trying to deliver, in that sense, I get to deploy my machine learning model. So yeah, it's really beautiful, and I never had the opportunity actually to try that on a cloud because my GPU is enough to build a transformer model from scratch using it. A very small one, but yeah, it works. So it was always enough for me, so I never had the opportunity to actually learn that. Deployments using Flask and stuff like that, these are pretty basic. We could do those within our software development sessions. So yeah, let's see what we can do with this, and let's learn something beautiful together. Now, we have the CRISP-DM framework. This has been thoroughly explained. Yeah, so now let's move forward and get our next candidate, which is modeling. Modeling, the machine learning, actually, we have something called the machine learning paradigms. The ML paradigms we have are actually four. So basically, we have the supervised paradigm, and we have the unsupervised. Okay, so let's talk first about the supervised. So the supervised is primarily concerned with, okay, I'm having those features and I'm having this target, okay? I'm having X and I'm having Y, and I have to connect both using the machine learning model training process. So basically, when I train a machine learning process to identify the identity of the speaker, basically I have the X as the MFCC features and the Y as the identity of the speaker, okay? So I get to connect both using a machine learning model that gets trained and actually has coefficients that actually reflect to give me Y as the output. Okay, of course, the Y predicted will always be different than the Y given in the data set or in the data that I'm given, but how close they are to one another actually is the whole point of the evaluation we have here, okay? So that is one example. Another example is predicting maybe apartment prices, okay? Based on different properties of those apartments or based on different features of those apartments. So this is the supervised. We have X and Y, and we seek to make connection between both using the machine learning models we got so that those machine learning models could get an X later and determine its Y without seeing it. And it could be as close as possible to the real thing. So that is the gist of the supervised machine learning paradigm. Okay, so why do we say paradigm, not a problem? Well, basically, the problem has an X and Y. Okay, so what if the problem has X and no Y? Okay, then it becomes an unsupervised machine learning problem. But that's not what I'm saying. The unsupervised machine learning paradigm is simply when I'm having data with X and Y, I get to deal alone with X. So I see it through the unsupervised paradigm to maybe process the data a little bit further to maybe decrease the features. So this is unsupervised machine learning problem. Okay, this is an algorithm that gets applied, that gets to understand the relations between features so that it actually could minimize them without losing too much information. So this is a feature extraction algorithm, an unsupervised machine learning problem. So it deals only with the X and not with the Y. So yeah, this is one side of the unsupervised machine learning problems. The other side would be clustering, which is like we have a bunch of data points and we get to cluster them in groups. Basically, people buying stuff at the supermarket, and you want to segment those customers into maybe 3 segments, and the model does that for you. But then again, you don't understand what's so special about those clusters until you do some data understanding upon them. So basically, you start with business understanding, data preparation, modeling, evaluation, and then when you evaluate the model, the clustering model, you actually find it to be performing very well. And so you have to go back using other metrics than the ones I mentioned, because there are metrics for unsupervised machine learning models. And in that sense, we get to go back to the business understanding phase and the data understanding phase to explore the data within those clusters specifically to actually determine the properties of such clusters. And in that sense, that would be very beneficial, okay? This means that the clustering algorithm is now giving us data mine. In the context of a supermarket, that's an example of the data mining. So in that sense, we have talked about the unsupervised machine learning paradigm, and we have a third paradigm, which is actually my favorite. It's really beautiful because, yeah, it's awesome actually. Self-supervised. Self-supervised machine learning paradigm is simply you have data all over the internet. You have a lot of data everywhere, and a lot of it is actually with a Creative Commons license. Like they can be used by any research team anywhere, and you get to derive stuff from them. So self-supervised machine learning paradigm is simply I'm having the X but not the Y, but I'm not treating it as an unsupervised machine learning problem. Why is that? So let's say I'm training a BERT model, for example, to speak to someone as an LLM. So in that sense, when I'm training it, I could be giving it the question and the answer, the question and the answer, speech logs, for example. Yeah, that would be actually very beautiful. And in that context, we could get those, and they're quite a lot. And on the other hand, we could get entire documents discussing specific concepts. And when we are training the model, regardless, we get to mask not the reply to the question, but to mask one word from a specific sentence and see if the machine learning model actually employs the multi-headed self-attention model that I told you about in terms of seeing every other word and realizing the word that is missing and substitute it. So basically the training of the machine learning model goes like that. I mask a token or I mask a word from a specific sentence, and I train the model to figure out a way to actually predict that missing word. And if it can predict a missing word, then it can maintain a conversation, in essence. So this is a self-supervised machine learning approach. It can be done programmatically to prepare the data. So basically the data preparation goes here in terms of the BERT, for example, in order to train it. So the business understanding is quite good in terms of the multi-headed self-attention model. Data understanding, not so much. And the data preparation phase is actually doing the masking of specific tokens and letting the machine learning model actually predict them. And in that sense, the modeling, we would train the model actually to predict the masked tokens. And guess where we have the real value of those masked tokens? We already masked them ourselves. So we already have the Y, but it wasn't originally there. So it is a self-supervised machine learning model. So like different training strategies, and all of them go well with the business understanding If we can predict the word, we can actually form a conversation. This is a business understanding aspect. This is the domain knowledge aspect. Okay, you get to employ your mental faculties and actually think of that solution. And in that sense, you get to devise a data preparation strategy to actually train the model based upon it. So, and we evaluate the model and deploy it, and there we go, the ChatGPT. Okay, so or the Gemini, DeepSeek, whatever. Anyways, the self-supervised, this one, and yeah, it's pretty good actually. So right now we have the reinforcement learning. I'm not having enough information or enough experience in that field. Except for the Q-learning problem, the usual basic stuff in the beginning of the reinforcement learning paradigm. But so I don't have enough information to actually explore in that as I've explored in other stuff. But let's say that, okay, reinforcement learning is we actually give the model or the algorithm every variable it can actually control and let it learn on its own to have a specific system that is complex enough to be controlled and that actually controls it. So how do you think Atlas, for example, the robot from Boston Dynamics, actually runs? Reinforcement learning, okay? It taught itself actually to stand on one foot. It taught itself how to backflip and do those kind of moves. Then again, it tried every bit of information itself in order to maximize the reward of its actions or decisions and to minimize the penalties. The reward would be to land on its both feet. To minimize the penalties, if I don't get penalized, then I'm good enough. And some kind of faults are actually penalized more than others for a robot and stuff like that. In maze solving, that could be done as well. But maze solving has like some pretty beautiful algorithms and data structures and algorithms as well that can be applied there. But then again, yeah. So this is the reinforcement learning. Maybe in 2 years' time or something like that, we could have explored every bit of thing here. Or maybe not, actually. It could take us years, actually, to discover everything with one another and work our way. And reinforcement learning is just a massive field. So maybe we will get in it one day and learn something new together. So yeah, let's see. Okay, so these are the machine learning paradigms we have through which we can look at the data and actually work with it to give to serve the business context well. Okay, so now I believe this concludes our session, but there is one extra thing to be given, which is each week we will deliver a session, God willing, that is focusing on theory, its practice on dummy data and on actual real-world data that we process using CRESP-DM framework. So basically, we will be discovering everything, and we will actually talk about theory in a manner that is respectful towards it, because theory gets brushed as unimportant or as mere intuition, but it's much more than that. Each equation, each formula, each operation, each term in this in a formula has its own character, has its own physical meaning. If you can get those connections, you can actually work your way in the domain knowledge understanding and actually come up with solutions that are terrific. Okay, you don't have to be a scientist to do so. So basically, in the Sprinkler distribution evaluator, I employed basic concepts in computer vision and applied them from scratch because it wouldn't be able to fit otherwise. When you learn everything from scratch, or to learn the essence of everything and to learn and to give due respect to its theory, it becomes beautiful. Like you suddenly become a more capable problem solver. So yeah, so basically each 2 sessions and then 1 session. 2 sessions, theory, practice, stuff like that, and hardcore theory actually, to understand every nook and cranny and the philosophy and the art of actually creating a mathematical equation. We will not memorize it. We will actually understand what makes a mathematical equation what it is. We intend to do so, God willing. So It's going to be awesome. On the other hand, we have on the third session, so each 2 sessions, we will have a third session that focuses mainly on software development. That's it, okay? And software development, it would be a hardcore software development application, not a complete application, but problem solving through programming is very important, and we could apply AI tools within our solutions. It's going to be awesome, God willing. So, and of course, with the 2 sessions that happen in theory, I will give free handouts that are detailing every bit of information that I've spoken about. So here we have 2 sessions, ML theory and practice. Then, so basically this is our schedule. Okay, and then we have 1 session, software development, with possible use of AI tools, but this is strictly possible, not mandatory to happen, okay? And then rinse and repeat, okay? Yeah, so that is our schedule for the course, and yeah, I'll see you guys next week, and let's do something awesome.